This is Euclid Book 3, proposition number 10, and this is probably one of the weirdest things you're ever going to see. First of all, you can see here we have a circle, and it starts at A, goes through B, comes down here to C. It'll go all the way around like this. It'll go through point O here. It'll go through point G. It'll come through point F. It'll go through point H, so on and so forth. Okay, so it's a perfect circle. But what you're also seeing here is an ellipse. And we don't say it's an ellipse right off the bat, but we're going to eventually prove that this is an ellipse. Okay? And this ellipse starts here at M, it goes through H, goes through D, goes through B, goes through E, goes through G, and of course there's another point it goes through, and you got to go through F, and it'll come back to M. So that's an ellipse. But we're not going to call it an ellipse right now. What we're going to do is we're going to say that suppose it's a circle. Obviously it's not a circle, but let's just suppose it was. Alright. Euclid says that no circle will cut another circle or even meet another circle at more than 2 points. And as you can see here, this ellipse here, that we're going to eventually figure out is an ellipse, meets at 4 points. B, G, F, and H. Alright. Euclid starts out by having you draw a bunch of funky lines. He wants you to draw a line from point B to point H, and again from point B to point G. And then what he wants you to do is he wants you to draw a line from KC, well, this is K, this is C, so he wants you to draw KC, and you're going to draw this through the center of the circle, which is going to be point P, and we're going to prove that later in just a second. Alright? Now, the way you draw KC is you have to bisect BH. And so BK becomes equal to KH. So these two lines are equal in size because we've just found the bisector. Now to find the bisector of BH, we have to use Euclid Book 1, proposition number 10 and proposition number 11. And you can do that for yourself if you like. Anyway, we find the center point K here, which makes BK equal to BH. And of course we extend K out from point K to point P to point C. Alright, then we bisect line BG, which is over here. BG is being bisected by L, which actually means that BL now equals LG. And then through point L, we draw a great big line that goes through P, goes through M, it goes through N, goes through M, goes all the way through O, and all the way through to E. Alright. Now, because of Euclid Book 3, proposition number 1, we can say that the line AC, this AC right here, cuts through line BH like this, okay? And it cuts it in 2 equal parts, and it cuts it at right angles. Then the center of the circle of ABC, remember ABC around here, is on line AC, which we have now said that that's going to be point P. Similarly, since NO, this is line NO, starts here at N, goes all the way to O, okay? Since NO cuts the line BG into 2 equal parts and at 2 right angles, then the center of the circle of ABC also lies on line NO. Well, line NO and AC intersect at point P. Now, that tells us the center of circle ABC, which is point P. We can use similar reasoning to prove, and if anybody wants to do that, that's great, but you can use similar reasoning to prove that the center of this second circle, which starts at H, goes through D, goes through B, goes through E, goes through G, goes through F, goes through M, so on and so forth, is also point P. And if we do that, we can say that point P is the center of 2 circles. And that's just impossible. Okay? And because that's impossible, then a circle does not meet or cut another circle at more than 2 points. And that's what Euclid was trying to prove. And if you want to do a better job of proving this, you're more than welcome. But now you have a pretty good idea of what Euclid was trying to do in Euclid Book 3, proposition number 10. I will tell you more in a future proof. Stay tuned.